All right, we're finally at the final video of this, what became a series that I thought could be one or two videos on the hidden subgroup problem, but it just turns out to talk about all the things for quantum computing, it takes some time. But today, we're finally going over, I guess, what you could call the heart of Shor's algorithm, the quantum Fourier transform over Zn for n equals 2 to the k, is how we're going to do it. But interestingly enough, you can do this for a multiple multitude of groups, for all the abelian groups and lots of non-abelian groups too. But you get these kind of recurrences. But the way to understand this is that in some ways this flattens basically the fast Fourier transform onto a quantum circuit. And what I found lovely is that if you open up like Aurora Barak, the complexity theory textbook, and you look at their quantum computing section in their chapter, maybe this is an old version, but like when I look up, they basically showed these sets of equations and then said, that's it. And didn't say that much else about the quantum Fourier transform. And the thing is, in this video, I'm not going to do all that different. I'm going to show these two equations. I'm going to talk about them a little bit. And I'm going to show this picture from Algorithmic Assertions. I don't know this blog, but they do have this great diagram of a quantum Fourier circuit over 1, 2, 3, 4, 5, 6, 7, 8, 8 qubits. And so I think this is basically a pretty good way to go. So to remind you of the fast Fourier transform, which you should have seen to understand this, is worth seeing, is in the fast Fourier transform, what you notice is that if I write down, here's a formula for the Fourier transform, f hat equals 1 over square root n, we're doing this factor so that's unitary, of f of y omega to the xy to the n. So I'm actually... see, my signs are slightly different. I would do omega inverse, but let's just go with omega. Why not? Because it doesn't matter. They're both roots of unity. So slightly different. I would write negative xy, but if you swap omega with omega inverse, it actually doesn't matter. So this is how defining the Fourier transform, that at frequency x, you sum over the y's, and you get this. And you notice, interestingly enough, that you can split it up into a sum of two Fourier transforms of size n over 2. That you could do instead the Fourier transform of all the even coefficients and of all the odd coefficients. Oops. And if you do this, this recurrence sort of defines how you can do it over in a clever way. This is how you reconstruct, but this is just another way of writing this equation again. That you, over the evens, when you go to higher omega, it wraps around, but for the odds, you pick up this minus sign for the higher coefficients. And so what you look at when you get this is in the typical fast Fourier transform, f of t, the input, this is a classical algorithm, is say n tuple of numbers, maybe complex numbers, maybe they're over a finite field, and you have some omega, a primitive nth root of unity. And then what you do is you break it down into two FFTs, two FFT subproblems of size, each of size n over 2. And the question is, how much work do you do on this? Well, you're doing about n work. You have to do this multiplication and do these powers. But really, for each y, sorry, not for each y, for each x, basically from 0 L dots to n over 2, you compute the f of t of the evens and the odds, and that will give you these summands here and these summands here. And for x from 0 dot 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 to n over 2, this works out fine. But from n over 2 plus 1 to n, then this formula still works out. Again, this is to check. You can check the equations. But you need to pass a minus sign here because not everything matches exactly the same. And that's what's being expressed by this right here. And so what you end up doing is you divide into two f of t's of size n over 2. You do n work in computing these sums and some multiplications. And after doing all this, let me move this. Might have to be slightly more clever with that omega to the x and how you do the multiplications out so that they distribute well. You'll get a recurrence relation that gets you to theta n log n work. For the classical f of t. It uses these same equations. So now what does it look for the quantum Fourier transform? Well, the quantum Fourier transform is really a subroutine for other quantum algorithms. And so your state is not represented as an n tuple of numbers. Your state is represented by, some underscore I equals, well, let's say x equals 0. 0 to n, and we'll put this in display mode because it's an important equation, of f of x, so it's stored in the amplitudes, x, over all these different strings. This is your state. And so what the quantum Fourier transform will do is very interesting in how it breaks things up. And maybe it's even time to look at this diagram here to see what's going on, because I can kind of see why Aurora Barak just says stare at these equations and see how it works, because I'm not totally sure how to walk through this well. You guys can let me know if I do well at all. But I'll just talk about maybe the thoughts I had while staring at these equations and doing it. And so, well, how do you get this recurrence in the quantum version? Well, you notice if I have this state, or if I have, let's call this equals colon psi, why not? Right? Well, I can write psi like this. Psi equals, let's call it psi 0. I'm just grouping up terms, and then everything that ends in 0. So this is the grouping, the superposition of everything ending in 0. And then I can write it psi 1, or angle, and I can have everything ending in 1. Okay. So psi 0. And this decomposition is how we're going to actually do the decomposition up here. Is that now, if we're sort of doing the recurrence going back, is that we can apply, again, our two f of t's, that this psi 0, you'll notice, is all the evens. And this psi 1 is all the odds. And so we can apply QFT here and QFT here. But remember, that we're working with quantum. So this is actually just applying QFT on n-1 on the first n-1 register as we recurse back. So we can apply the QFT on both of these, and then what we'll get out is we'll get the QFT values here, and then 0, and the QFT of the odds here, and then 1. And so we can actually readily compute, these sums, the f of y and f y even and y odd. Then the last thing to do is to reconstruct using these, because the problem is you need big capital N entries here, but when you do these QFTs, you get n/2 values out of it. But because of the way it works, wrapping around the circle roots of unity, all that means is just adding the same thing, plus n omega to the x for low coefficients, and then picking up a minus side for the higher coefficients. And so how do we do that? Well, now I think is the time to look at this. So what's going on? Well, this Hadamard matrix actually expresses ft high. We'll say ft, how do I write this? ft low, ft high, if we think of this as a column vector, which I'll call ft, is equal to h, the Hadamard matrix applied to ft even and ft, well, w ft odd. That if you look back at the Hadamard operation, do I have it written down nicely somewhere here? Maybe all the way back here. Yeah, here's the Hadamard operation. And so you'd have to renormalize, but it is renormalized. It's just written without normalization here. That you get that our final Fourier transform, the final thing we do is this Hadamard on ft even and ft odd after applying w, funnily enough. And so that's why we get this Hadamard at the end. And then what's this dot, and what are all these z? These are these are roots of poly z quantum logic gates. I also opened up the quantum logic gate Wikipedia page, which is fun to look at. And you can see what this control does. What the control does, and you can see here, so here is a controlled knot, is that it says if this thing is 1, if we have a 1 value here at this bit, then we will apply the operation. So here's the C naught, we'll apply naught. Otherwise, if it's 0, we'll do nothing. So it's the identity matrix. And so controlled Z, oh, they show controlled Z here, great. If it's 0, we multiply by, we do the Z operation, and which is this 1, -1, which all it does is it picks up a -1 on the 1 qubit and does nothing to the 0 qubit. But if it's not, we do nothing. And if you notice, essentially what this big chain of controlled Z's ends up doing is it actually encodes this factor right here. That essentially x, all of our coefficients, going from the most significant bits at the bottom, we reverse it, so the most significant bits at the bottom, down to smaller and smaller significance, that if we take omega to the x, basically if it's a highly significant thing, that's this big power of 2, and that will end up multiplying by z to the half, which is I, and then this will multiply by z to the quarter, which is square root of I, etc., down, if and only if we have a 1 in that digit, in that qubit inside the superposition. And so most of the work that actually happens here is done in the multiplications of the omega to the x here on reconstruction. And then the Hadamards, what they do is they express this sum right here, that ft is hft even times wft odd. The controlled, why is this controlled? That it only happens corresponding to the 1 qubit? Well, it's because you only want to count these contributions and apply this z on the odds, because otherwise, if it wasn't controlled, if you were just doing z's, you would also have a factor of omega to the x here, and you'd get the wrong value. So I gotta say, for me understanding this, even though I know the fast Fourier transform, and I'm reasonably comfortable with these things, let's just delete all of this, put that back. I'm reasonably comfortable with all these things. I gotta say, when I first saw this, the way I understood the quantum Fourier transform is I looked at these equations and I stared at the circuit for like an hour and a half. And because it was rather confusing of like what's really going on, and you really have to see that like when I'm applying these operations, like when I apply the controlled z or any operation to a superposition, that operation happens to each and every one of the summands. And so it feels like you're doing control logic here. You're doing, if the qubit equals 1, do this. And it's like, are you doing branching with your quantum circuit? That seems odd. But really, what that does in practice is it applies that multiplication on the odds, and it doesn't apply the multiplication on the evens. And so that controlled, that if logic breaks it up between these two summands. And then why is it this poly z on each of these different gates? Well, that corresponds to like if the bit representing this x is equal to 1, well, we know the amount of contribution to omega to the x we're going to get. And so we multiply it if basically both this is a 1, and if the qubit here is a 1, because the poly z is only applies to the 1 qubit. So what does this all add up to? Well, in the FFT case, we get this FFT gets into 2 half-size FFTs plus n work, and that turns into n log n time. Here, we get a size, we start with the size n QFT, and it seems like we do 2 n over 2 QFTs. But again, because of the magic of superposition, that's actually just 1 QFT, because it disappears into the superposition because we apply that QFT operation. Like looking back at this, you can put a box around all of this omega to the x and Hadamard reconstruction, and then we have a QFT starting from right after this Hadamard. And so instead of it being 2 n over 2 QFTs, it's actually 1 n over 2 QFTs. And then how much work did we do? Well, we have to do work for each of these. And so we do order log n work plus log n work. And if you solve this recurrence, this gives you theta log n squared time. If you want to be careful, you can be careful with like how much all these operations, and you actually get these log logs and log factors. Maybe the log matters. I don't think the log factor is worth mentioning. But in terms of the input size, this is an n squared quantum algorithm. You could call it tilde O n squared. And this quantum Fourier transform over 2 to the k, which really, and all the other quantum Fourier transforms look like this. They look like you take some recurrence coming from the fast Fourier transform for that group, and you transform it into something like this. This is just the simplest example. And I guess that really is the capstone for this, because I'm not sure what else to tell you. I would say if you're interested in learning more about quantum computing, I can link some more things. I might make a random video about mixed states, because I was thinking about the true state space of quantum states and the like. And if people are interested, I can do that. And I might do a quantum computing video here or there if something random comes up. Maybe I'll do quantum key distribution, BB84, because I think that's worth talking about. And it is different. It is a lot of, in the previous videos, I talked about, uniform state, apply function, Fourier transform, sample. A lot of quantum algorithms sort of look like that. And quantum key distribution is different and interesting. And so if that's something people are interested in, let me know. But the real magic of what goes on is that it's really that you can leverage the superposition here. And that I feel like you can see it more clearly in the previous video, what's going on with quantum algorithms. That you can see more clearly that you can filter out and find these frequencies still there when you apply QFTs. But yeah, if you feel like you don't understand this, that's fine. It took me a lot longer to understand it. And I think, again, especially with technical stuff or in math, you have to be participatory. So I think you just have to kind of sit down and look at these equations, and you can open up Aurora Baroque or any resource on quantum Fourier transforms and really think about what's going on. Like you can think, why do you reverse the digits here? Why does this circuit end up giving you the quantum Fourier transform with the significant bits reversed is another question that you can ask yourself to see if you're understanding what is going on. I think the other one useful is seeing how do we get exactly the right omega to the x factor by applying these controlled poly z's. So this control applies to all of these z's, not just individual. And why does it happen on these wires? But yeah, that wraps things up. Good, and finally,